Now we are going to study another approach to do the clustering, which is density-based clustering. And after that, we are also going to briefly look at how to validate if we have done the clustering well. So when we are talking about density-based, the criteria is that there should be a connectivity through sufficient density. So this way we will be able to find if there are natural clusters which are of arbitrary shape. And since we are talking about density, it is likely that the noise or outliers cannot impact because it is likely that those points are fewer compared to the natural data. And the density-based clustering methods can get the significant information in the one scan, as we are going to look at one of the algorithms. And we need to define here some density parameters as the termination conditions where we'll be satisfied with the quality of the clustering. And as we can see here, there are several interesting algorithms which make use of the density-based techniques. And the density-based techniques depend on two parameters mainly. One is called epsilon and the other one is called min points. So whenever we are looking at the neighborhood, let's say we are looking at the neighborhood, then we want to be clear what is the distance that we consider as the neighborhood. So that is the epsilon, that is representing the radius which we consider as the neighborhood. Then this is possibly the distance which is representing the neighborhood. And then we will look at the number of points that are available within the neighborhood to say whether this point can be classified as a particular form. We are going to see what is the way we are going to term a point when there are sufficient number of neighborhood points. And there is a definition of a density reachability. So we can say that a point P is density reachable from point Q only if P falls within the radius of Q, which is represented by epsilon, and Q has minimum number of points that is represented by the min points within this radius. Then we say that P belongs to the neighborhood of Q, which we call as a epsilon neighborhood of Q. And in this case, the important point is that there should be more than min number of points within that epsilon neighborhood for Q. Then we say that the P belongs there. P belongs to that, is a density reachable, directly density reachable from Q. And there is another associated concept which is a density connected. So while the density reachable means that we have a chain of points, for example from Q to P, here it is not directly within the epsilon radius of Q. But then it is within, from Q there is a point P1 which is within the epsilon radius of Q, which has got the, and Q has got the minimum number of points within its the radius epsilon distance. And but again for P1 we consider the same criteria, that is the P1 does have another, when we can look at the radius, we are looking at the epsilon radius and min points, and through that you will be able to reach P. So here as you can see that P is reachable from Q if we have a set of points P1 to Pn such that Q is the first point, and then from Q we are, and at each Pi and Pi plus 1 we should have a condition that satisfies that Pi plus 1 is directly density reachable from Pi. So in that case we are going to reach that point through set of points. And another kind of form of connection that can exist is that if two points are directly density reachable from a third point, then we call that as a density connected relation between these 2 points. So we can say P and Q have a density connection if there exists a point O such that both P and Q are directly density reachable from O. And the dbScan is a density based algorithm which makes use of these parameters. And dbScan defines three types of points. One is considered core point, another one is considered the border point, and the third one is considered the noise point. So it is considered core point if it has a minimum number of points within the epsilon radius, and it is considered a border point if it is within the epsilon radius of one of the core points, but it does not have the minimum number of points within its epsilon radius. And it's considered a noise point if it is neither a core point nor a border point. So this is how it looks like. As we can see here, this is a core point for the minimum points of 4, because what we can see here is that within its radius we have got 3, 5 and so 6. So we have got 6 points within its epsilon radius. So this point is a core point. Now if we consider this point and when we draw its epsilon radius, what we see is that we have only 3 points within its epsilon radius. So what it means is that it is a border point, considering that it is a point within the epsilon radius of this core point. Let's say this is A, this is B. So B is within the radius of A, but B does not have a sufficient support within its own radius, so it cannot become a core point. Now if we look at point C has neither. So point C is not within the radius of A, nor it is having its own, it can be considered a core point because it does not have a sufficient number of support. It has only 2 points within its radius, epsilon radius. So in this case, the C is becoming a noise point. So dbScan treats these 3 types of points in a different way. So now if you look at a dbScan algorithm, first thing it does is that it eliminates all the noise points. So now it is left with only core points and border points. So what it does is that it does it for all the core points. For each of the core points, it is checking whether there is a cluster around it. Otherwise, it is creating a cluster and with this core point, and it is assigning the cluster label to that core point. And then whenever a cluster is created with a core point, all the points within the epsilon neighborhood of this core point are going to be assigned to the cluster that is created. So we continue this until there is no core point is left without any cluster label. So dbScan, if we use the dbScan and define these core border noise points, as we can see here, if we look at this is the original points. If we classify the points as either core, border or noise, and using the color green is representing the core points, and then blue is the border points and red is noise point, we can say that it is doing a pretty good job of differentiating to start with the data space. And after that, it applies the algorithm. So it works pretty well when it has got a clear cut of noise for which it has to filter, and then if it has to create different shapes, if there is a sufficient density, it can work simply with the density. So thereby, if we reduce the epsilon and then there is a sufficient density that there are minimum points within the epsilon radius, then we will be able to create in fact a cluster of any shape. If there is a natural cluster based on the density, then we will be able to capture it by giving a suitable parameters, which is the epsilon and the minimum points. But as we can see, there are 2 parameters, and by varying those parameters, we are going to get a different set of clusters. So as we can see in this example, so if we used a minimum points 4 and an epsilon of 0.5, we got clustering of this form. Once we reduce the epsilon further, we started dividing this natural cluster into multiple clusters because it looked at a density within this cluster, and then it differentiated them based on that. And here again what we are seeing is that here we can see that though we are seeing the 2 net structures which are looking like rhombus, And but within that, each structure, we can see that there is a variation of density. We can see that some places there is a lighter density and some are with a heavier density. So that is going to, if we have got a sufficient high epsilon, we are creating a natural cluster as expected. But once we have once we asked for a lower epsilon for the same minimum points, then based on the density we have differentiated these clusters, and the number of clusters became different with the decreasing epsilon. And this algorithm does not work well if a single shape has varying density of points within it. So once we used a different epsilon, we need to choose a suitable epsilon if the density is varying. And also it is not suitable when we have a high dimensional data, because the definition of a density is going to be a challenging parameter. And to find out what is an optimal epsilon and optimal min points, we may do a data analysis initially. For example, here we have got let's say 3,000 points. What we did is that we plotted a graph which represented the distance within which we have the fourth neighborhood exists. So that is within what radius we are able to find 4 points. And then we plotted this. So now if we think that there is a line beyond which it is likely to be a noise, then we can suitably define the epsilon and then min points, and thereby we will be able to get a good density based clusters. Now let's look briefly about how to validate the cluster analysis that we have done. If we have got some set of clusters, how do we know that those are representing a good segmentation or clustering of the data that we have? So for when we had a supervised learning, that is classification, we had one advantage. Suppose that we had 100 data points which are representing the training data. We could easily choose 70 points to represent the classification model and other 30 points to validate the classification model, because these 30 points have got the correct answer within them. So we can validate and say that this model is good and so on. But with cluster analysis, such a luck doesn't exist, because cluster analysis is not done with some preconceived ideas or any parameter in mind, or with a definite answer in mind, because in that case we don't call it cluster analysis. So the result of cluster analysis, to say whether it is good or bad, it is in a way, it is depending on what you think. So we need to we need to look at the cluster analysis goodness from certain parameters. For example, we know that some points are noise. So is it able to eliminate that? And also we may be able to use the cluster analysis to compare two different cluster algorithms. So as we have seen, when we compared them using the various parameters, then we found that one clustering is better than the other form. And we may also compare with the sets of clusters and draw a conclusion. Or we may be able to look at two clusters and see that how are they looking like. So one cluster may be too small compared to the other one, or it is representing a different level of density compared to the other cluster. So that will help us understand where is the cluster analysis algorithm that we used is giving us good results. So some of the aspects when we consider when we validate the cluster analysis is that first thing we look at is the ability to form non-random structures that are existing within the data. And then if we have an externally known results, like the way it happened in classification, then we may be able to use those known results to see whether the cluster analysis is done well. And we may be able to do the cluster validation without a reference data, in that case, we only use the data that we have used to do the cluster analysis. And then we may have two different sets of cluster analysis that has been performed, and we may want to compare them, and thereby we want to find what is representing a real natural number of clusters within the given data. And as it happens, as we can see here, 2, 3, 4, we may consider that for the entire clustering or for the individual clusters. Let's say we are doing the cluster analysis on a medical data. So the researcher is interested in finding out, let's say, a drug resistance for some of the patients based on some symptoms, or another researcher wants to know whether some patients or some people are more prone for a particular ailment. So in such case, the result may come without doing a complete cluster analysis, because their focus is on finding one individual cluster that helps them draw some conclusions. So in that case, this point can be applied. So same thing happens with the third and fourth one. For one particular cluster of our interest, we can see using the internal data that is matching all the requirements of us for forming a cluster, or for example, for let's say for a target marketing, then we may be satisfied. And some of the measures for cluster validity, for the external measures, they are more like the classification measures. But in case we want to depend on the internal index, that is, we don't have the external labels available whereby we can identify the cluster's goodness, we may want to use the sum of the squared error, which depend on the distance metrics, and then the distance metric itself depends on the type of attributes that we have, and if we want to give any weightage, etc. And we may use a relative index, so that we may use to compare different clusterings or the clusters. And sometimes we may want to go with the matrices to know whether we have done a good job with clustering. So let's say we created a proximity matrix, which is representing the n by n matrix. We have n data points, we find the proximity of these points to every other point. And then we create an incidence matrix which is built after the clustering is done. Here we create an entry of 1 whenever the associated pair of points belong to the same cluster, and 0 if they belong to different clusters. And then we will be able to do a correlation analysis, because we have got the two matrices of the same size, and thereby we can determine if there is a high correlation. Then we may say that the cluster analysis worked out well. But if we have a challenge of the contiguity based clustering, we are looking for a particular shape clustering, because we can see a natural cluster of a particular shape based on density and contiguity, etc. Then this correlation may not work well, because it considers the relation between all the points based on the same criteria, whether they are together in the same cluster or not. It doesn't bother about their actual distances to create the correlation, and then it never considers the n proximity. For example, whether there is one point which is in a dense neighborhood and another point which is in a rarefied neighborhood, it doesn't consider those points. So to that extent, this may not be reliable. And finally, the cluster validity is still an evolving field. We do not have a very solid outcomes with respect to how do we find out, how do we know whether one cluster analysis is better than the other. So the validation is still a big challenge.